So before I jump into the slides, I brought some show and tell here. So this was the stock focuser on the RCs that we typically use. Mine is a 12-inch. So the 10 and up have this larger 3-inch focuser, and the smaller ones I think are 2-inch. So this is what I've been imaging with for the last year or so, and prior to that, this same motor rig was on my 8-inch RC, and that's a Rigel Systems that you can retrofit on here with the gear that fits on behind this knob. We'll talk about focal reducers, but I've been using the Astrophysics CCD T67. It's kind of a standard focal reducer that people use with these RCs. So that's what focusing and focal reduction looked like, and now it looks like this, which is the whole talk tonight. So this is a moonlight focuser, on-axis guider from Innovations Foresight. There's a ZWO cooled CMOS and a filter wheel, and another ZWO cooled CMOS for the guiding camera. So we'll go into all of that. And the reason that this is on the very first slide, micrometer, is because all the measurements and everything become super critical when you're putting something like this together. So get started. So we're going to talk about backfocus because that's critical to this whole thing, what that means, and that leads us into focal reduction. And also touch on some different focuser options for this particular scope and others. And then we'll get into the actual on-axis guiding device right here with the cold mirror in it and how that all works, how that came together with my need for focal reduction, then some results that I've gotten to date and what my conclusions are. And then I'll give a parts list, and there's also an appendix with a bunch of other stuff that came up during this project that I thought would be interesting, might be helpful for you guys. Okay, so it's all about backfocus. When you're adding stuff to your imaging train, it's all about, how much space do you have between where your prime focus is and where your focuser is able to place your imaging rig. So we need to look at focal reducers, when I'll tell you why in a minute, but to understand that, we need to understand what this backfocus thing is. So all of these RC scopes that we buy come in various brands, right? TPO, GSO, Astrotech, Orion, they all come from the same place. They come from the same factory. And so, Jerry, how many extension tubes do they come with? Three. Okay, Jerry just got his. And I'm teasing him because he didn't think he had any, but he had 3 like he's supposed to. So between this, the focuser, and the optical tube, they have usually 1 large and 2 little extensions to move this around. And the reason for that is to come to focus without any focal reduction or any other nonsense in there, you'd need that focuser to be all the way out. And then as you start to add stuff back in, especially focal reduction, you'll be taking those extensions out because your prime focus is going to move towards the OTA. So, which is what I just said. Yeah, so as you add stuff, especially the focal reducer, either because you've got more hardware that you need to fit in there, or because you're actually moving the prime focal plane with the focal reducer, you'll need to move that focuser in closer to the OTA. So filter wheels, off-axis guider, flip mirror, focal reducer, field flattener, all that stuff has to fit in there somewhere. And so it's also possible that you have so much stuff that you want to put in your optical train that you actually run out of room and you can't come to focus anymore. And so that whole thing is called backfocus. Okay? And so that's most likely to happen with focal reduction because that's actually moving the focal plane towards the optical tube. So let's talk about focal reduction, and we'll use this diagram over and over again here. So focal reducers, they're also called telecompressors, focal boosters. They're basically the opposite of a Barlow, right? So a Barlow you'd want to use for planetary, it's going to magnify things. Focal reducer is going to do the opposite. It's going to spread things out. So this list of stuff here that it does, they're really all the same aspect, right? Or different aspects of the same effect, right? So it's going to make your scope faster. It's going to reduce the focal ratio of your scope. It's going to shorten the effective focal length. It's going to increase your field of view. It's going to decrease your scope's image circle. It's going to increase your image scale, in other words, arc seconds per pixel, and it's going to decrease your exposure time. So those are all really the same things, but that's the effect of a focal reducer. And you know, I showed the one in the middle there is the CCD T67, which most people use on these scopes, and then the one on the, here I can use my new toy, maybe. This guy is the one that I'm using in here now, the Astrophysics 27 TVPH. Okay, so again, focal reduction, it's a positive lens. It's going to shift the focal plane inward towards the scope. And looking at this chart, you see the reducer right there. It's going to shift this focal plane from where it was originally in towards the scope. And the way that you control how much focal reduction you have is by controlling this distance here, the distance between the camera sensor and the focal reducer's optical center. That controls how much focal reduction you have. Then adjust that. Then the things that change are, you know, this distance, how much it shifts, and this distance, where the focal reducer needs to be for things to come to focus, and also then the effective focal length of your rig. Okay, so why would we want to do this? You know, I just bought this big scope with a lot of magnification or what have you. Why do we want to then change the optics of that? So as an example, let's look at my latest setup here. It's the 12-inch truss. So that's the 12-inch aperture then. It's a native focal ratio of f8. There's the focal length. They don't really spec the image circle, but most sites have it somewhere between 30 and 35 millimeters, and that's kind of depending on, you know, it's going to have some curvature out at the edges, so it depends on, you know, how much curvature you're willing to tolerate. And, you know, so why did I buy this scope? Well, I bought this scope for the aperture, and my theory was that it would help me with imaging from a light polluted place like Union City, where I live now. You know, the reason I buy the RCs is for the aperture per dollar, basically. So I have trouble with the French Richie Chrétien. It's two people who invented this particular optical design. And what this optical design is, it's the same optical design that's used on the Hubble, and it's got basically two hyperbolic mirrors. So there's the light comes in, and it goes down here, and it hits the 12-inch mirror, which is hyperbola, and that reflects up here to a secondary mirror, which is also a hyperbola, and then it goes down through this tube and out the back, and your camera's out here somewhere. So the light actually goes through there 3 times, and so the focal length of the scope is basically 3 times its mechanical length. So the RC is shorthand for the Ritchie Chrétien, and it refers to this design versus a Newtonian or Schmidt-Cassegrain or other types of reflector telescopes. All right. So if we then look at what camera I wanted to put on this, I'm using one of these new-ish cooled CMOS cameras, a ZWO ASI 1600. And so it's got really small pixels, and the sensor isn't huge. But what happens is, if we use this CCD calc here, there's other tools that you can use to do the math. But you end up with that camera and that scope native, you end up with a field of view of about 19 by 25 arc minutes, an image scale of 32 arc seconds per pixel. And we'll note that that's much less than the rule of thumb of 1 arcsecond per pixel that you need to have good sampling in what is typical amateur seeing around, amateur observing sites, which would be 2 arcseconds per pixel if you're lucky. So and the other thing that this CCD calc does for you is it gives you a little picture here with the FOV on target, and you can select different targets, but we're all familiar probably with M42, so I put that there. So this FOV is okay. It's probably a little on the small side, but I think 2 bigger concerns for me in designing this was, one, this sensor size is a lot smaller than the image circle of the scope, so I feel like I'm wasting light. I feel like I spent money on this big scope to get the 12-inch aperture, and I'm only, sort of sampling a part of it. And the other thing is that oversampling that we talked about. So, 32 arcseconds per pixel is probably way overkill. So by using focal reduction, we can move it more towards an ideal setup for this rig. So again, using the focal reducer, you need to do some amount of planning. With certain focal reducers and certain scopes, like with SCTs, that's a whole different optical setup with a moving primary for focusing. The focal reducer goes on the back, and it is what it is. It's a certain 6.3 or f3.3, and you can't change it. And the distance from there to your sensor you can't change, and that's just how it's set up. But in this case, with the RCs, you can control how much reduction you get, again, by that distance here, this x1 distance between the optical center of the reducer and the focal plane of the imaging sensor. Adjusting that controls then how much this thing shifts and where everything lands, and you may run out of backfocus, or you might have too much field curvature if you try to have too much reduction. So I keep referring to this chart over here. So this is a web page, and you'll notice here that it's on my hard drive. It's not out on the internet because this page got retired at some point. This guy down here at the bottom has copyrighted it, but it's not published anymore. So I used the Wayback Machine to borrow that, and I've tweaked it a little bit to have the scopes I use and the focal reducers I use in there. Yeah, and then I've also added some more parameters in the output. All right, so let's do an example. So still not worried about the ONAG or any of that stuff. So typically people use these astrophysics CCD T67s with these RCs, whether it's a 6-inch, 8-inch, 10-inch, whatever. That's typically what they use. So again, using CCD calc, let's say we wanted to do a 0.7x reduction. Now we've got an FOV that's quite a bit larger. It's 27 by 36, and we've got our image scale up to 0.46 arcseconds per pixel, and we've shrunk the image circle down to closer to what the image circle of the sensor diagonal is. So we're using more of that light from the scope. So now we've got an effective focal ratio of f5.6. We started with 8, and the focal length then changes as well. So you could go for more reduction, but you're probably going to start getting curvature at the edge. The stars will start to stretch out into the corners. Okay, so yeah, we're still oversampling by quite a bit, but at this point, if we wanted to have that rule of thumb of the 1 arcsecond per pixel approximately, we could take an array of 2 by 2 pixels as 1 pixel, and that would get us closer to that number. Depending on who, I gave a talk a couple months back about whether you should or shouldn't bin in this situation with CMOS and all that. So take your expert, but either way, I've just been going bin 1. So we've talked about, again, controlling the amount of reduction with the spacing. So if I go back to here, you'll see that it says that X1 needs to be 91.5 millimeters. Okay, but that's the distance from the optical center all the way to the camera sensor. So how do I then implement that in the real world? So, you know, the focal reducer itself, from the where the lens is in here to the threads, is 16 millimeters. And then you have to account for everything else between that and the camera sensor. So the ZWO filter wheel is 20 millimeters. And the flange focal distance, that means the distance from the mechanical front of the camera to the actual sensor, is 6.5 millimeters. So you add all that up and subtract it from the 92, and it turns out that you need to add 42.5 millimeters of, or it's the other way around. You need 50 millimeters of spacers, right, extension tubes. So that looks like that. And then even with all those 3 extensions that I was teasing Jerry about off the back of the focuser, in order to achieve focus, I still had to shove that whole assembly. This here where it says 16.5 millimeters is right about here. It just happens to be facing the other way, or you can see that label. So that whole thing has to be shoved into the draw tube via this compression ring, you know, to about there, in order to achieve focus. So if I had any more focal reduction, any more space between here and the camera, I wouldn't be able to achieve focus unless, you know, I'd have to shove this in even further, I guess, would be the solution there. So that's leads you to kind of, well, what about thinner focusers, and what are the pluses and minuses of different focusers? So, you know, this is the stock focuser. It doesn't cost anything additional other than the $350 to do the motor controller solenoids. And it's got a fairly low profile. It's only 70 millimeters. And then this Moonlight that I ended up with, in its thinnest configuration, this is actually what they would put on a SCT Edge, is 98 millimeters. And then if you've got more money than I had, what everybody wanted to sell me was an Optec Leo for $1,800, which is only 32 millimeters thick. And then, you know, if you really wanted it, if you wanted a rotator and focuser, then you can get your wallet out for that. So hopefully you get what you pay for with some of these other focusers. So the way I had originally wanted to stay with the stock focuser, and that's one of the reasons we'll talk about in a minute why none of the telescope stores were willing to really work with me, because they all wanted to sell me that Optec Leo and tell me that you can't possibly image with this stock focuser because it's so lame and it could slip, I guess, if you put too much weight on it. I've never had any problems with it, but they didn't even know that, you know, Rigel Systems had a motorized system for this. They're like, oh, you can't even, you know, automate that focuser. And anyway, whatever. So, okay, let me pause for breath here. So, back focus, focal reducer, any questions on that stuff before we get into the ONAG? Yeah, I don't know how well that would work. You know, in general, I said earlier that you need to have a focal reducer that is either designed for your scope or that other people have said works well. So I would suggest, you know, go into AstroBin and search for your scope and search for that focal reducer and see if anybody's using that combination of stuff. I mean, the way I picked my first equipment was looking on AstroBin, and, you know, I had an idea. You know, I thought I wanted an RC, which, don't get me wrong, I mean, it's bang for the buck, but it's also, as a first scope, it's very challenging because it's got such a long focal length, right? So other people would argue that you want to start out with a small refractor and everything's less critical. You've got a much bigger field of view. It's easier to find stuff. It's easier to track all that stuff. But I kind of jumped. I didn't want to, you know, how many pictures of the North America Nebula can you take, right? So I wanted to do deep space, so I jumped in. But yeah, so I looked and saw who had, you know, used the scope I was interested in, and I saw that they were using the CCD T67, and I saw what kind of images they were getting, and so I felt pretty comfortable what kind of mount they were using. I felt pretty comfortable that I should be able to get some good stuff. So that's one way to do it. All right. Anything else on focal reducers or back focus? Okay. Yeah, what I really wanted to do was implement one of these on-axis guiding things from Innovations Foresight. Bruce and I saw Dr. Gaston Baudet at the last two AIC's Astroimaging conference in San Jose, and it was really intriguing, and he's doing a lot of interesting stuff, and I think there's more to come, but it all rests on you having this hardware. So we'll get into some of that. So what is this thing? So if you've ever seen a flip mirror, so a flip mirror is a box with a mirror at 45 degrees in there. So it's kind of like a diagonal, but a flip mirror, this mirror flips up or down, and that way you can select between an eyepiece and a camera, or between two cameras or two eyepieces or whatever. That's a flip mirror. So this mirror is fixed, but it's what's called a cold mirror or a dichroic beam splitter. So what it's doing is it's reflecting the visible light up to your imaging camera, but the near infrared goes through to your guide camera. And because that's, it comes in two sizes, but you buy it based on your image circle. So you've got, basically your whole image circle available for the guider, versus an off-axis guider where you just have a little pick-off prism or something that's only a little piece of your field of view. The other thing that happens, because the near-infrared is going through this filter at a 45-degree angle, there's some astigmatism, and it turns out that there's some properties of that you can take advantage of to do autofocus, and we'll talk about that. So these bullets here are Gaston's marketing stuff about what this thing does for you. So it gives you, a wide field of view for your guider. It does have these nylon white plastic screws are the guiding stage. So this thing does move around. So you could move the guiding stage to select a guide star. So far I haven't had to, which is really cool. And I'm hoping it remains that way, because I've got a fairly big sensor on here. It's not as big as the imaging camera, but it's fairly big. So that's an advantage over off-axis guiding. As an advantage over a separate guide scope, you don't have any differential flexure. You're looking through the same scope that you're imaging through, so you're guiding what you're imaging, right? There's no difference in alignment or flexure as things change over the night, angles or temperature. There's some advantages to guiding in near infrared. So one of the things I had done when I first read about this was I went out and got a near infrared filter and put it on my guide camera, and it did help, even though it was a separate guide scope. It does seem to help. There's less high frequency noise, and that allows you to image lower on the horizon and all kinds of stuff. Yeah, so you're saying you don't have to, an off-axis guider, you might have to rotate everything to find a guide star, which means, you've invalidated your flats, or you changed your image orientation of the camera. Maybe you don't want that. So in this case, you don't have to do any of that. Depending on how you had your things set up, there's no filter in the way. Your filter wheel here is, just on the imaging port of the ONAG, so the filters are not in the optical path for the guide camera. What else? And then he talks about the autofocus, which we'll talk about. So that's happening all the time in real time. It's not waiting for a certain temperature or for a filter change or anything. It's just always in focus. He's got the next thing that he's working on is multi-star guiding. So rather than picking a guide star, it's just going to take the whole frame, look at a bunch of stars, so that you don't have to worry about picking a guide star at all. So he's got that software out in beta. In fact, it's a whole imaging suite, but you can buy it in pieces. You can buy the focus piece and the guiding piece and the imaging piece all separately. But right now it only works with Maxim DL, which I don't use. And so they're supposed to be coming out with a new version that works with Sequence Generator Pro, so I'm kind of waiting for that. But in the meantime, it works with PhD2. So again, here's what this looks like on the back of my scope in my yard. So the full frame guide star using PhD2, the near-infrared guiding. And because we talked about that light passing through the cold mirror on an angle, you get this astigmatism, which changes the star shape, which means in software you can look at that star shape and figure out whether you're in or out of focus. And this SkyGuard is the combination of the guiding and focusing software. He has a Sky something name for each of the modules, so SkyGuard is for those two modules. And again, I'm waiting for Sequence Generator Pro. So this is what that astigmatism does. So, you know, your imaging bouncing off that mirror, the visible light looks normal, but if you look at it through the guiding port, it's going to have kind of a cross shape because of the astigmatism. And when it's out of focus in one direction, it turns into a sort of a horizontal line, and when it's out of focus in the other direction, it turns into a vertical line. So you can use that. He's got software called Focus Lock that is from Optech, actually, that then can connect to your focuser through the ASCOM driver and dynamically adjust that all night long. So one thing I didn't do research carefully enough in reading all the manuals ahead of time was there's one issue that you can have a problem if you've got a large center obstruction. Well, let's see, I've got an RC with a 50% obstructed, you know, the secondaries covers 50% of that mirror. F6 or lower, well, geez, I'm trying to do focal reduction down to about F6. And I added, because I found out the hard way, if you've got small pixels, that's also a problem. There's also kind of a bit of a catch-22 here in that you need to be roughly in focus in order to get guiding going, because if you're trying to guide against a star that looks like that or looks like that, you're not going to get very good guiding, right? So you kind of have to be close. So what I've been doing is I just go ahead and use SGP autofocused V-curve to get me there, and then turn all this other stuff on, and it locks it in and keeps it there the rest of the night. And you have to have PhD2 running and guiding in order for the focus lock to get its image. So it's actually getting its image of the guide star from PhD2. And it only happens when you're actually guiding, not just when you're looping. So you have to keep that in mind as well. Okay, so let's talk about some challenges I had in putting this together. So the first problem is that everybody wanted to sell me that really fancy Optech Leo thin focuser. They didn't want to talk to me about trying to get it to work with the stock focuser. It just can't be done. Another gentleman I talked to was convinced that I'd have horrible vignetting if I tried to use this focal reducer that I selected and, you know, have the ONAG SC, which has T2 openings on it. So it's a 2.7-inch wide focal reducer going down to 42 millimeters in only about, that much space mechanically. Optically, it's about that long. He's like, there's no way, it just won't work. And I'm like, I've done the math and I've got the diagrams, and he's like, it can't work. So anyway, that's part of it. And so just adding the ONAG by itself is non-trivial, right? There's lots of measurements that you have to take and lots of clearances that you need. So this is one of my sketches, and if you look, some of the clearance, here's the ONAG, and if it's going to go this way towards the focuser, and you've got this big filter wheel up here, you have to make sure the filter wheel isn't going to run into your focuser or your scope. What happens here between whatever adapter you have and the ONAG, you need a little bit of space there, and then you need space if you want the guide stage to be able to freely move in all directions the maximum amount it's designed to, then you need some space between the top of the ONAG and the filter wheel. So all of those clearances have to be arranged, and he's got, Gaston has some very confusing spreadsheets and some web pages that I thought were also confusing, but there's lots of that you have to go through. But then, I had to make it harder by wanting to do focal reduction, right? And so the way they expect you to do focal reduction is, put a focal reducer here on the imaging port in front of the filter wheel and put another matching one here on the guide port, and that way both cameras would be in, looking at the same thing and be in focus. But the problem with that is, I don't have the back focus for that, because the ONAG is 66, 68 millimeters in one direction and 90 millimeters in the other optically, and so there's not that much space with the focal reducer. The ONAG would have to be somehow down inside the focuser or something, right? Remember how in this case the focal reducer had to be down inside the focuser, so if this ONAG was on the front of the focal reducer, that's obviously not going to fit down inside there. And then, so the other possibility would be to put the focal reducer with the ONAG sort of in the middle. So you could put the focal reducer on the scope side, and then, the ONAG becomes part of those extension tubes between your imaging camera and your guide camera. So the problem with that was, again, that 68 millimeters in one direction and 90 millimeters in another compared to, 50 millimeters of the design, right? So the ONAG is too big to fit with the focal reducer. So I had to find a different focal reducer that had a different focal length that was more gentle, that would allow to put the ONAG in that space. And that was another thing that, oh, you crazy, you can't do that, it won't work. So I looked at all the focal reducers on every web page I could find, and I found this astrophysics one, which has a 700 millimeter focal length, and it looked like it would work. So yeah, I couldn't use the CCD T67, so I found this thing. So some challenges with that. It's 2.7 inch threads, so it's not, you couldn't do this with a focuser smaller than 3 inches or maybe 2.5 inches. The nose of this thing is about just under 2.5 inches. The threads are 2.7. So the smaller RCs, 8 inch, 6 inch, would not work with this focal reducer, because you can't get it down inside the focuser unless you replace the focuser with a bigger draw tube. So that's one of the, when we get to the chart again, the web page that does the design, that's one of the parameters of a focal reducer, is its focal length and its diameter of the optical diameter. Those are the two parameters. So it's a positive lens, so it has a focal length like a telescope. And so, well, yeah, let me jump all the way back here. So the CCD T67 is 305 focal length, and this one is 700. So what I did at this point, since everybody was still telling me I was crazy, is I went ahead and I bought the focal reducer just by itself, and I had to promise that I wouldn't try to send it back if I scratched it or marked it up in any way. So I did buy it, and then what I did was I just put extension tubes in there to simulate the optical distance of the ONAG. And so again, by using different lengths of extension tube to figure out different amounts of focal reduction and where I would run out of back focus and which focuser I could and couldn't use at that point. Yeah, so I bought the focal reducer, and then I had gotten talked into this Moonlight focuser, and in its stock configuration, there was just like no way it was going to work. It was just too tall, so that had to go back and get reconfigured. And then also, there was an adapter that went, the draw tube of the Moonlight is 68 millimeters threads, and the adapter to go from that to the astrophysics 2.7-inch threads, they're the only ones that have that particular standard, was too thick to where the whole design wouldn't work. So I had to get one from Precise Parts that was thinner. So speaking of which, so now I've ordered 3 things from Precise Parts. I ordered an adapter to make on the stock focuser, which I'm not going to use, but I wanted to be able to use it if I wanted to. The compression ring comes off, and so I bought an adapter that threads into the draw tube, and this whole thing could then sit on that. Here on the left is the 68 millimeter to Astrophysics 2.7, and then I also needed on the other side of the focal reducer, I needed to bring that down to T2 for the ONAG. And so I put this here in case you're curious about Precise Parts. So you go to their website, and it's a 2-step process. In the first step, you just kind of put the brand, like I want to go from Astrophysics something to something else, and you put those in, and you put your desired length, and if you want it to be the minimum length, you put 0, and then it's going to tell you what the minimum length is. So we're looking at the second step of both of these where the design is finished. So it's showing you here, this is what it's going to look like. And if you click on this guy here, you get a 3D model that you can rotate and look at from all sides, so you see what you're getting. And then it tells you what the optical distance is going to be and what the price is going to be. So, and then it takes like 3 days, and you have your part. The only downside is it's pricey. Okay, so one gentleman was convinced that I was going to have this horrible vignetting. So this is one of 3 different sketches I did to try to convince him of tracing the light, through this thing to show that I wasn't going to have vignetting. And he said, "I don't care, it's not going to work." So here's a test shot that I did with the spacing, no ONAG, but just the extension tubes between that new focal reducer and the camera. This is actually a 4-panel mosaic, which has nothing to do with the project, but it was just something I was working on. So anyway, it works. So then, this is where, if I wanted to keep the moonlight, everything was going to be super tight. I was only going to have a millimeter or 2 of focus left, inward travel on the moonlight. It's just going to be super close. And in fact, I was using a different filter wheel with different filters, and I have 2 other filter wheels now at this point, and they're both thicker than this one. So I ended up having to make this all work, I had to go with this ZWO filter wheel, which is only 20 millimeters. And I had a ZWO filter wheel with ZWO filters in it. And as some of you may know, they have a halo problem on bright stars. And so I took this opportunity to replace those as well with Astronomical 6 nanometers. So at that point, the ONAG arrived. And so it turned out that it was still too close. And one of the problems was this mechanical diagram on the right here with the big knot sign through it is wrong. So at least for the guide camera that I have, maybe it's an older model, but it's completely different than what is shown here. So its flange focal distance is different. This is showing that the flange screws on with screws. Mine threads on. And it's a whole different piece here on the front, and so that just threw everything off. So I was stuck. I was bumming. So the only thing I could do at that point was to use a smaller guide camera that would fit down inside the helical focuser on the ONAG guide port here, just like in a guide scope. And so I grabbed the camera from my external guide scope and put it on there, and then faced the next challenge, which was I had guide stars with a hole in the middle, even when they're in focus. So this green set of green lights here is telling me that Focus Lock thinks it's that's the best focus it's going to get, but there's this hole in the middle of the star, which makes it very confusing for PhD2. to do good guiding. So apparently the fix for that is to reduce the amount of astigmatism, not eliminate it, because you need astigmatism for the focusing. But Innovations Foresight will sell you this handy little lens that corrects for the astigmatism to a certain degree, and you can adjust it. But the problem is it completely fills the inside of that helical focuser, which meant that I couldn't then use the camera that was in there, so I was still stuck. He also, Gaston, had me using at that point, because of this hole in the star, a special version of PhD2 that apparently they didn't adopt his alternate algorithm. So it's sitting there several revs back from where PhD2 is now. And so I was kind of stuck and frustrated. So a couple things worked out. So it was time to pull a rabbit out of something. So what I needed to do was somehow, push the focal plane of where things come to focus out further away from the ONAG so that I could use this guide camera that would be outside the helical focuser. And at that point, I thought I would need to buy that astigmatism reducer. So I had to clear that space, right? And so how, I can't, if I increase that space, it's increasing the space between the focal reducer and the camera sensor, which is going to shift the focal plane in, which means I'm already out of, I've only got 1 millimeter or 2 of inward travel, so I can't do that. So what do I do? So, I'm just sort of staring at this for a long time, and then I figured out, well, one thing I could do, this is the back side of the, helps if I, back side of the focal reducer here, and it's got this like 10 millimeters of thread depth here. And here's my adapter, which is only using, about half of that. So I looked in the phone book, not the phone book, of course, but, looked on Yelp or whatever, picked a machine shop out of the air, and went over there and said, "This is a telescope part, could you please?" So we had a good long, hour-long conversation, and he charged me for a half hour, and we milled off 7.9 millimeters of threads off that thing, and saved the threads were still viable when we were done, which is good. And so that meant the ONAG could move forward by that almost 8 millimeters, and so relative to the ONAG, now the focal planes have moved out by almost 8 millimeters, which allowed me to then achieve focus with this guide camera outside the helical focuser. Then I caught another break when so that was success, ta-da! And so this, I'll talk about the pixel size of the camera in a minute, but so success, yay! So yeah, we milled that thing down, and so I added a little bit of space between the filter wheel and the imaging port, which meant that now I could have both cameras come to focus. I still have about 1.5 millimeters of focus left compared to, this is my critical focus zone, so I'm okay there. And so then I did an image. So here's the bigger crescent there is one I did from Union City over a couple nights. And I was guiding in about half an arc second RMS. So there was 53 8-minute HA exposures, 4703, and then I put some RGB stars over the top. So look at that one, and then compared to one I did with that same rig. Now there's lots of differences between these two. It's not good science, but it's the same rig from Scotts Valley where I used to live, which is darker. So shorter, only 2.5 hours total integration time. And, they're not processed identical, blah, blah, blah. But anyway, I think the new one looks a lot better. And we'll go into some metrics. And that's what you're supposed to see, right? You're supposed to see, both the improved guiding and improved focus is supposed to make things pop. You're supposed to see more detail and tighter stars, and everything gets sharper. So we will come back to the guiding. So what did I end up with image scale wise? So I'm shooting at f 6.3 I keep hitting the wrong button. F6.35 is where I ended up. And here's what the field of view looks like. I've still got a pretty big image circle. Now, one thing I learned about these calculations here is this is sort of a back calculation. It doesn't really have anything to do with the image circle of the telescope. It's just telling you what the focal reducer is going to do relative to its diameter. So I'm still kind of tweaking that part, but anyway. So guiding results. So I've noticed I have like super huge signal to noise ratio now with this near infrared guiding. You know, it's typically like around 200, which is crazy. You know, you see these stars and you don't see any noise at all. It's just boom. And I haven't had to move the guide stage, so now I think I've done 3 or 4 targets and I haven't had to move the guide stage, so that's good. You know, I passed the log to the PhD 2 guys when I was working with that hole in the star thing, and they declared that, hey, you know, you should stop stressing. Your guiding is probably scene limited at this point, right? And so, you know, I'm looking at this, and I'm very happy with, you know, my RMS here. This is not good. And then in looking at analyzing the log, you know, there's some stuff that could be cleaned up with periodic error correction. So the next step was to, you know, I hadn't rebalanced the mount, right? So I'd taken off the guide scope, I put all this new stuff on, and I hadn't changed the balance. So I went back and did that, and there are some learnings there, which we'll talk about at the end. Took off the guide scope, added the ONAG, rehomed it. I intentionally checked but did not repolar align because I have a certain amount of backlash, and one of the things we'll talk about in the appendix and learning from this is you may want to have a little bit of mispolar alignment if you've got some backlash. Keep your guiding all in one direction. As it's turned out here, even though I've got, according to PhD 2, bad backlash, I'm still seeing limited, so I'm not stressing about that. So I re-recorded the PEC, and that improved. This is the thing you have to know about this graph versus the last one is the scale's about half as much, so, you know, the noise peaks went way down. So now I'm, you know, 0.4 RMS, and, you know, my peaks are the worst one is 0.76 arc seconds. So, I mean, that's a solved problem in my view, right? I'm not gonna worry about guiding anymore on that. And then as far as autofocus goes, so this is, you know, again, the focus lock's view of the guide star when it's in focus. And now notice the hole is not so bad anymore. That's because I have bigger pixels, I think. And then it has these charts that is really for troubleshooting when you have problems, I guess. So these are guiding frames. So I was guiding at 3 seconds. So each, you know, 100 times 3 seconds would be the time period there. So you can see it when it's initially adjusting, and then over the night it's making changes. And these were two different nights, different situations. So what are the focus results? So using a couple different tools here, this is FITS image grader at the top. So I've got, you know, pretty much scene limited focus there, and really small deviations. So that's good. And the PixInsight is telling me the same thing. This is the full width half max, except for some clouds. And I know these are clouds because of my cloud sensor project. And then the deviation is also small in PixInsight. So this was across multiple nights, different target altitudes, air mass, etc. It's holding the focus. Another way to look at that, and again, you know, this is not good science, but comparing those two images, they're processed images, so kind of all bets are off. But if I just pick a star, same star in both, so before I was doing SGP autofocus and that 2.5 hours from Scotts Valley. The star profile looks like this. It thinks the scene was pretty bad at almost 12 arc seconds. You know, the half width, half max, 5 arc seconds. The star had a radius of 17. So now, with the focus lock, 2.77 arc second scene, 3.42 is the star profile with a radius of 13. So, you know, it's much sharper results. Then I wanted to just understand, why was it making those adjustments over the night? Was it temperature? What was it? And so I graphed it, and these error bars represent the critical focus zone, and they really could be twice that big, right? Because this is the whole critical focus zone, so you could argue that it could be off on one side of critical focus by the whole amount. So I could have made those bigger, I guess. But anyway, there's, you know, it's kind of a rough correlation to temperature, right? So this is the ambient temperature, and this is the focus position. So then I looked at some other parameters, and it's kind of interesting that there seems to be kind of two groups of data in all of these charts, and it's basically on either side of the meridian. So my conclusion is there's something in my scope that's shifting a little bit when it flips, does the meridian flip. There seems to be some weak correlation here with the air mass, but I don't know, not enough data. But point is, it's in good focus. So what are my conclusions? So I got scene limited guiding with no need to move the guide stage, at least so far for the targets I've looked at. I've got consistent sharp focus. When I made this slide, I said I was going to go back and check it with a Batinoff mask, which I did, and it actually made it worse. So the V-curve in SGP turned out to be a better way to do it. So I do the V-curve to set the imaging camera in focus, note down what that focus position is, and then there's a helical focuser here on the guide camera. So I set it up to autofocus and then adjust this until it arrives at that same focus position that the V-curve said was the best focus. So that's the technique I'm using. With the moonlight temperature sensor, I also have my sky sensor has an ambient on it as well, but I just used because the one on the focal reducer ends up in the FITS header, so it's easier to do that. So, you know, it would have been easier to have a thinner focuser. So if I could have thrown more money at this, decided to live with the stock focuser, then things wouldn't have been quite so critical. But overall, I think it was worth it, the cost and the effort. I'm very happy with the results. So that is that. And I've got some more information here. So second image, I just posted this today. It's a little corner of Pickering's triangle, or another way to say it is it's a very, very small piece of the Veil Nebula. But anyway, I just thought that was cool. I might do a mosaic or something, but anyway. So that's another bicolor, and then RGB stars over the top. So parts, right? So for the 12-inch Truss RC, we had the Moonlight focuser for large RCs with the high-res stepper motor. It comes with a mini V2 controller, except that they reconfigured it to with these options to make it as small as possible. Then I needed the precise parts adapter to go from that draw tube to the astrophysics focal reducer. On the other side of the astrophysics focal reducer, we shaved 7.9 millimeters off, and then we had a precise parts adapter to go to T2, which goes into the ONAG. Then on the imaging side, a spacer, the filter wheel, and the camera, the imaging camera, and I have both monochrome and one-shot color cameras that I can swap here. And then the ASI 174 cooled on the guide port. And it turns out that you know, those bigger pixels helped, and I didn't have to get that astigmatism. So I'm going to pause for breath again. So I have some other stuff to talk about, but any questions about the ONAG or anything we've talked about so far? Yeah, so originally the filter wheel that I had planned on using originally, so I have other filter wheels. I have a filter wheel that's 2 inches and has beta or narrowband in it, but it only has 4 positions. And then I have a ZWO that's got LRGB and narrowband, but it's only got 7 positions. And anyway, my thinking was that I couldn't use the filter wheel with the color camera, so I was going to replace the optical space of the filter wheel when I'm using the one-shot color with a spacer. And I started to do that the other night, and you know, that meant I was going to have to refocus and everything. And then I realized that, well, there's an empty filter position in this filter wheel, so I could just shoot through that. In theory, the camera would thread on to the same exact position as the other camera, which turns out not to be true, but so you still have to refocus, but close. But then I also realized that, you know, anytime you go through glass, it does shift your focal plane a little bit. So I decided to just shoot through the luminance filter, which is roughly the same thickness as the narrowband filters. So that's what that was. It doesn't have anything to do with the infrared. It's because I had one, and it turns out in PhD2 in the latest versions, and they might have to be dev versions, but you can control the camera, because I didn't. That's another thing I hadn't thought about. Oh, I've got a cooled camera, but I didn't think about how am I going to turn it on. So you have to have some software to control it, right? So that's now in PhD2. So that there is, and I think it's in the appendix, there is a mini version of that same camera that would have fit inside, but it's not cooled. And again, I thought I was needed to be outside because of that astigmatism thing. So, and yeah, I didn't want to buy another camera too. So this camera, well, also it's a very good planetary camera, although I haven't done a lot of planetary, but that's the reason why this camera exists. But it selected that for guiding, not just because I had it, but because, excuse me, the pixels they're 5.8 something microns, so they're bigger. You kind of need that, and it's a fairly, it's not as big as the imaging sensor, but it's a fairly big sensor compared to a typical guide camera. So otherwise, if you have too small a sensor, then you're going to be moving the guide stage all over the place, which when I was using that QHY camera, you know, there was never more than one guide star in the field of view. But I've been using it with a near-infrared filter all along. So I'll put the focal reducer calculator up there, still tweaking the image circle piece, I guess, but because the way it is at this URL is actually goes the wrong direction, the way the guy had it originally, I noticed. As I said, the latest PhD2, at least the dev versions, can control camera cooling if you've got a cooled camera. It's on the brain under the camera specific information at the bottom. You can have a set temperature and either on or off. So as Bruce advised me, you probably don't want your camera cooler running during the daytime, so you could have SGP disconnect all the guiding devices when the sequence ends, and that would shut the cooling off at the end of your sequence. So one of the learnings from this whole thing with the stock focuser was nobody knew that there's an adapter sitting here between the compression ring and the draw tube. Nobody knew that came off. They just thought this was one piece. And what that means is it's technically possible to put something like that 27 TVPH focal reducer in here. It wouldn't fit through here. And so I did buy another precise part. It's just on this side just to store it. But so now Precise Parts knows about that, and they know what the threads are, and they can build adapters. So if for some reason you want to do something with the draw tube of your big RC stock focuser, you can now do that with precise parts. I had hoped these threads looked like they might even be that astrophysics 2.7, but they're not, that they're close. But close is led to that discussion where the guy said, now, if you try to thread that in there, you're going to screw up the threads, and don't try to return it to me. So, all right, what else? Yeah, so yes, there's a mini version of that camera. I'm aware of that, but you know, I had those challenges with thought I needed the astigmatism thing. I at one point was wanting, you know, like a helical focuser on this side on the imaging port, and did research, and there are helical focusers that don't rotate, and there's one that's 11 to 18 millimeters is the thinnest one I could find, which is still way too thick for this project. But if you had a thinner focuser and had more room to move things around, that might be a handy thing to add in. So just FYI. Then another thing I noticed regarding camera cooling and whatnot was I had never scrolled down PhD2. This window here was always cut off, and I had never bothered to scroll down to see all this information that they had here. So it's got your image size and your field of view, and then the camera cooler information at the bottom. So I just redid my UI to have that displayed all the time. So that's what it looks like now. There, and then what else did we learn? So in rebalancing the scope, you know, the scope got lighter, so I was moving the counterweights up, and I thought, well, geez, maybe I can get away with 2 counterweights instead of 3, and I wonder what the better situation is. And kind of, I've always thought, turns out incorrectly, that less weight on the mount in total would be a good thing. So I'd rather have fewer counterweights out at the end of the counterweight bar. This is assuming the counterweight bar doesn't flex, which is also not the case. Seemed like it would be a better idea. Let me just post, you know. So I posted on cloudy nights, hey, what's the best thing? And I got back this whole, you know, like 6 guys pointing to different references, all in agreement, and all saying that's wrong. You want the counterweights up as high as possible because it has to do with the moment arm. Or let me get it right here. It's not the, you know, I was just thinking about the force arm, but they're talking about the inertial moment arm because it has to do with the distance squared. So basically what you want to do is you want to have more counterweights and you want to have them up as high as possible. So they're suggesting that you put your counterweights all the way at the top. This guy is the correct way, and then you have a small one that you use to do your fine balancing, and that this will actually put much less inertial, make it easier for your mount to make guiding corrections because the inertial moment will be much less than if you had this situation. So who knew, right? So at that step where I rebalanced and my guiding got better, maybe part of it was because of moving the counterweight. So I have since ordered some more counterweights and will continue to push mine higher and see if it, but I have to keep reminding myself that guiding is really a solved problem now, so I should stop trying to make it better. But anyway, there you have it. Okay, then one more thing. So this is a little off topic, I guess, well, for the ONAG, but another thing that came up was, you know, let's say you've got deck backlash that you can't fix in your mount. So, you know, and I had different people looking at my guiding. So Gaston, Dr. Baudet, was saying, yeah, you want to just mispolar align a little bit. That'll force you to guide deck in one direction only. And so I'm like, well, okay, misalign by how much and in what direction? And so I wrote to the PhD2 guys, and they're saying, yeah, they, I think it's this one. Oh, it's here. He's saying, yeah, it doesn't matter which direction, just a small error, a couple arc minutes, and then increase your min move. So those are things that you could try if you've got a problem with backlash. And I think I had a follow-up. Oh, yeah, because then he says, but if you are misaligned by too much, then you have field rotation. Okay, so how much is too much? So then there's you know, websites that do that calculation, and stuff for you too. So that information is in here, although I didn't end up following up on it because I was, again, guiding became a solved problem. Okay? Yeah, it doesn't matter apparently. So what I did when I rechecked my polar alignment with a PoleMaster, at where it says press start monitor, so it's roughly aligned, and then you go in to the fine tuning. So in the fine tuning step, it was just at the outside of that circle where it wants you to put things together. So it was just, and then PhD2 was in guiding assistant was telling me that it was 1.7, 2.1 arc seconds off. But if you look at my, and I did mess around a little bit with the min move, but it just made things worse. So I'm guiding in deck, changing directions, and I'm still, this one says 0.41 arc seconds of RMS. I'm not going to mess with it. The only thing I know is he said because it's doing it at an angle. That's all I know. Don't claim. You do not get, I don't know. I mean, we could go look and see. From my memory, that's all he says is because it's coming through at a 45-degree angle. The image part's reflecting off the surface, and the guiding is going through a lens, essentially, at a 45-degree angle. Did I measure? I don't know how to do that. There's that astigmatism corrector has some numbers associated with the 3 different settings. I don't remember what those numbers are. If you go to Innovations Foresight, he's got some education pages where he goes through all this stuff, but I don't know if you're going to get the level of detail, but you can certainly email it. So what I've been doing is I turn the focus lock off. I do a V-curve typically with H alpha, because I figure that's the most important thing for me, right, in SGP, and note down the focus position. So let's say it's 290. Then I'll start up guiding and start the autofocuser and start focus lock and get that all running, and it'll go off and change that focus position to something else. And then I'll take my laptop outside and sit by the scope and turn there's a helical focuser on the guide port here, so loosen the lock screw and turn that, and then watch and see where it settles, and I do that until it settles at that same position. 290 was the example, so that they're both methods are saying the focuser should be at 290, and then I'll just let it go the rest of the night like that. And when I come back the next day, whether because I've maybe moved the camera in the process of putting the cover on my scope, or because the temperature's different, or because it's been meridian flipped and back and parked, it's usually different, but I don't have to redo that process as long as I haven't changed any of the spacings here. If it's way out, I'll do the V-curve and then start focus lock, but I'm saying I won't readjust the helical focuser. It's good like it is once you set it.